the basic definition of moment of a force about a point. Which means if this is the line of action of a force, this is the line of action of a force, call it F, and there is a point O, then the moment of this force about O, the moment of this force about O is going to be given by F into D, where D is the perpendicular distance of the line of action of the force from the point O. D is also referred to as the moment arm. D is also referred to as the moment arm, right? And the moment about O is given by the product of the force into the perpendicular distance of the line of action of the force. This is the line of action of the force from the point O. This perpendicular distance, D is the perpendicular distance from O to this line of action, right? And like I said, you know, the force F. So this also qualifies to be an entity that is responsible for creating a turning effect. Responsible for creating a turning effect, in the sense that, you know, if O was, let's say, part of a rigid body like this, and the rigid body was hinged about O, you would expect that the turning effect produced about O in this case is this way. If the rigid body is hinged about O, and if a force is applied like this in the plane, then F into D is the turning effect. And do you see the sense of the turning produced? Anti-clockwise. So in this case, ACW or anti-clockwise. ACW or anti-clockwise. So in this case, anti-clockwise, right? And then suppose I had a force, the rigid body was hinged about O, and this was F. In this case, if this was D, the moment of the force is going to be F into D, but this time it's going to be clockwise. It's going to be clockwise. Clockwise turning effect, right? Now, there is a body that could be acted upon by very many forces. For example, you know, if this is a rigid body, for example, and you know, we are going to look at planar situations. So all my discussions for the time being would be confined to moments of forces that lie in the same plane as that of the rigid body. So this could be a laminar or equivalently a planar situation. Now, say there is a rigid body hinged at the point O, right? And this is a force F1 acting on the rigid body. This is a force F1 acting on the rigid body, and its perpendicular distance from O is D1. Its perpendicular distance from O is D1. And say there is another force F2 acting on the rigid body as shown, and its perpendicular distance from O is D2, right? Now realize that this F1 produces a clockwise turning effect, which is F1 into D1. This F2 produces an anti-clockwise turning effect about O, which is F2 into D2, right? Now we can look upon the whole thing as a net turning effect. Whether under the influence of these two forces there is going to be a clockwise turning effect or an anti-clockwise turning effect. For that, what we say is, all right, let's adopt a sign convention. And it's your choice. We can say all anti-clockwise ACW turning to be deemed as positive and all clockwise to be deemed as negative. Anti-clockwise positive and clockwise negative. Now, so the net turning effect. So this F2 into D2 is anti-clockwise, say, so plus. And then F1 D1 is clockwise, so minus F1 D1. So this is the net turning effect. This is the net turning effect, or the net moment about O. This is the net moment about O. And if positive, if the net moment about O is positive, then the net turning effect is anti-clockwise. That means the net turning effect is anti-clockwise because we have taken anti-clockwise positive. And if less than 0, then the net turning effect is clockwise, because we have taken clockwise to be negative in the sign convention, right? Or if it is equal to 0, then there is no turning effect, and when there is no turning effect, we say there is rotational equilibrium. When this happens, we say there is rotational equilibrium. We say there is rotational equilibrium. Rotational equilibrium. That means the algebraic sum of the turning effects is 0. That means F2 d2 minus F1 d1. If this turns out to be 0, then we say it's a case of rotational equilibrium. Rotational equilibrium, that means F2 d2 turns out to be F1 d1. That means F1 d1, as you can see, is clockwise. The clockwise turning effect. F2 d2, as you can see, is anti-clockwise. That means if the net anti-clockwise moment turns out to be the net clockwise moment, then the net moment acting about that point is 0, and there is no net turning effect, and we say it's a case of rotational equilibrium. It's a case of rotational equilibrium. Yes or no? Right? So which means when we are talking of equilibrium in general, then we are talking of total equilibrium. We are talking of 1, translational equilibrium. 2, we are talking of rotational equilibrium. So if we are talking of total equilibrium, then there must be translational equilibrium, there must be rotational equilibrium, right? Translational equilibrium means the vector sum of all forces must add up to 0. That will guarantee translational equilibrium. And rotational equilibrium means net moment about any point in the plane must be 0. About any point must be 0. So if a body is in a state of total equilibrium, which means this is true for sure, then if net moment about one point is 0, then we can show that the net moment about any other point will also be 0. So you can take moments about any point in the event of rotational equilibrium subject to presence of translational equilibrium. If net moment about one point is 0, then net moment about any other point would be 0. That's guaranteed. And that means net moment 0 means the clockwise moments must add up to the anti-clockwise moments. The clockwise moments must add up to anti-clockwise moments. So I repeat, if a body is in a state of total equilibrium, so 1, vector sum of all forces acting on it must be 0. That will guarantee translational equilibrium. 2, rotational equilibrium. If that's true, then the net moment about one point being 0 will guarantee net moment about any point being 0. That means the algebraic, the sum of clockwise moments must be equal to sum of anti-clockwise moments. The algebraic sum of moments must be 0. If we choose all anti-clockwise positive and clockwise negative, then algebraically they must add up to 0. Right? So that's the story of rotational equilibrium, and as of now we are restricting ourselves to planar situations, right? Now let me look at a very simple example. What's that simple example? So let's say there is a rod AB, uniform rod AB, One more thing that you must understand is that if there is a force F and its line of action passes through a point O, if the line of action of a force passes through a certain point O, then the perpendicular distance of O from F must be 0 and the moment about O must be 0. That means if a force passes through a certain point, it will produce no turning effect about that point. If the line of action of a force passes through a certain point, its perpendicular distance from that point will be 0 and it is incapable of producing any turning effect about that point. So we will use this fact again and again. Now, suppose there is a uniform rod AB and of say mass 10 kgs, of mass 10 kgs. That means weight could be looked upon as 10 kg weight. 10 kgs is like force 10 into 10 newtons, 100 newtons, G is 10, or we can also say it's 10 kg weights. It's like a 10 kg weight force. We say it's like a 10 kg weight force. Now, suppose the rod is of length L equal to 2 meters. The rod is of length L equal to 2 meters. And it is supported at 2 points. There is a point P and there is a point Q. It's supported at 2 points P and Q, right? Say P is 1/4 of a meter from A and Q is, say, let me draw it a little further. Q is, say, 0.3, 3/5, 0.6, okay, 3/5 of a meter. This point Q is 3/5 of a meter, say. Right? Now, if this rod is uniform, then it could be imagined to be a point mass at its midpoint. It could be imagined to be a point mass at its midpoint, and through this point a 10 kg weight will act because of Mother Earth. A 10 kg weight will act because of Mother Earth. We want to be able to find the reaction forces at P and Q, assuming that those reaction forces are vertical, so that AB is in equilibrium. In order to keep AB in equilibrium, let's say the reaction force at P is R1 and the reaction force at Q is R2. Let's say this is in kg weight. Right? So every kg weight could be mapped onto newtons, or every newton could be mapped onto a kg weight by using a factor G, which is acceleration due to gravity. I want to be able to find the values of R1 and R2. Now, clearly this body is subjected to 3 forces, R1 and R2 parallel, and weight, 10 kg weight, anti-parallel with R1 and R2. 10 kg weight anti-parallel with R1 and R2. Surely, for equilibrium means 1, all vertical forces must cancel off. That means R1 plus R2 must together support 10 kg weight. Yes or no? R1 plus R2 must together support a 10 kg weight force. A 10 kg weight force. Right? Now, if there is rotational equilibrium, in addition to translational equilibrium, if there is also rotational equilibrium, then the moments about any point must be 0. The net clockwise moment must be equal to net anti-clockwise moment. Now, this point, this whole thing is 10 meters, so this is like 1 meter from this end. 1 meter from this end, and this is like 1 meter from this end. 1 meter from either end, right? And this is 1/4 of a meter, so this is like 3/4 of a meter. 3/4 of a meter. This is like 2/5 of a meter, because this is 1 meter, this is 3/5, so this is 2/5 of a meter, right? I want to be able to solve for R1 and R2. I want to be able to solve for R1 and R2. Now there are very many ways. So one thing, I could have taken moments about the point M, and I could have said all clockwise moments must be equal to all anti-clockwise moments for rotational equilibrium. Suppose I take moments about M. For rotational equilibrium, moments about M. Moments about M. So do you realize this R1 produces a clockwise moment about M, and what is it going to be? R1 into 3/4? And this 10 kg weight passes through M, so it produces no moment, right? So this is R1 into 3/4. This about M produces a anti-clockwise moment, as you can see. A clockwise moment, as you can see. A clockwise moment, right? About M, it's going to produce a clockwise moment, right? What about R2? R2, so this is clockwise moment about M, right? What about R2? Realize that R2 about M will produce an anti-clockwise moment. Will produce an anti-clockwise moment. So that's going to be R2 into 2/5. This is the anti-clockwise. And the two must be equal so that they could cancel off. So that the net moment about M is 0. So we very clearly have from this 15 R1. 15 R1 is 8 R2. That's my second equation. That's out of considerations related to rotational equilibrium. This is out of considerations related to translational equilibrium. This is out of considerations related to rotational equilibriums. Now all that we need to do is to solve for R1 and R2. Alright, so what I can do is write in this, I can write R1 plus R2. R2 I could have written as 15 R1 by 8. That's equal to 10. Or we have 23 R1 equal to 80. 23 or R1 equal to 80 by 23. 80 by 23 newtons. That's R1, right? And if R1 is known, obviously R2 is 10 minus R1. So 10 minus 80 by 23. So this is like 230 minus 80, 150 by. This is not newtons, this is kg weight. Because I have looked upon R1 and R2 as kg weight, because this 10 kg is also 10 kg weight. So R1 and R2 are also kg weight. So it's not newton. R1 is 80 by 23 kg weight. And R2 is 10 minus 80 by 23, 150 by 23 kg weight. Alright, so we've obtained the value of R1, we've obtained the value of R2, right? Now that we've obtained R1 and R2 by deploying, of course, there is no other way we could have written equations for translational equilibrium. There is only one way. But as far as rotational equilibrium is concerned, subject to translational equilibrium, nobody restricts you. We took net moment about M as 0. That means all clockwise moments adding up to all anti-clockwise moments, right? So that their algebraic sum is 0, and we obtained the values of R1 and R2 with the help of say 15 R1 is 8 R2. We solved for R1 and R2, and we got the value of R1 as say 80 by 23 kg weight, and we got R2 as 150 by 23 kg weight. Right? We could have taken moments about any point, not just M. We could have taken moments about any point. For example, what could we have done? We could have done the following. We could have taken moments about Q. Let's take moments about Q. Realize that R1 will produce a clockwise moment about Q. How much will that be? That's going to be R1 into 3 by 4 plus 2 by 5. 3 by 4 plus 2 by 5, that's clockwise moment produced by R1, right? Weight, 10 kg weight, this produces an anti-clockwise moment about R2. So that's like 10 kg weight into 2 by 5 into 2 by 5, right? That's anti-clockwise about Q. And R2 produces no moment about Q because the line of action of R2 passes through Q. So this is the net clockwise moment about Q, and this is the net anti-clockwise moment about Q, and they must be equal. They must be equal. So if they are equal, let's see what R1 turns out to be. So that, why should they be equal? Because their algebraic sum must be 0, right? And that is what would guarantee rotational equilibrium of this rigid body. So we have R1 into, say this is 15 plus 8, 23 divided by 20, right? 15 plus 8, 23 divided by 20 equal to, this is 4, equal to 4. So that gives me R1 equal to 80 by 23 kg weight. Now of course if you want to convert into newtons, you can multiply by G. So R1 is 80 by 23. Yes, we got R1 equal to 80 by 23. Yes or no? We could have taken moments about any point. If somebody just wanted R1, you could take moments about Q. If someone just wants R2 without obtaining R1, one could take moments about P. One could take moments about P and obtain R2. Yes or no? So this then brings us to some very important, very relevant and very pertinent facts on moments. But let me illustrate a little more to get you comfortable with things. All right, can I wipe this off? Yes, let's do that. Now let's let's check this out. Suppose there is a cylinder. And there is a step of height h. There is a cylinder and there is a step of height h. O is the center of the cylinder, and let's say R is the radius of the cylinder. R is the radius of the cylinder, right? And say W is the weight of the cylinder in newtons. Say W is the weight of the cylinder in newtons, right? And this is the point of contact with the step. This is the point of contact with the step P. And there is a force that I apply passing through O parallel to the horizontal. A horizontal force F is applied. Horizontal force F is applied whose line of action passes through the center of the cylinder. Now, what is the minimum value of F so that the cylinder climbs the step? So that the cylinder climbs the step. That means at P, you know, pivoted about P, it will climb the step. That's what I'll assume. Now realize that the forces acting are F, and there is weight acting downwards like this, as you can see, right? Very clearly, this F about P will produce a clockwise turning effect. F about P, as you can see, F produces a clockwise turning effect about P, whereas W produces an anti-clockwise turning effect. W produces an anti-clockwise turning effect about P, right? So very clearly, if the clockwise effect just about exceeds the anti-clockwise effect about P, it's going to climb the step. There is reaction force at P, but it produces no moment about P. So it will not hinder with the clockwise or the anti-clockwise turning effect produced by F and W about P, right? Now, evidently, as you can see, this is the radius R, right? This is H, so this is also H. So this length is very clearly R minus H, because this is R minus H, right? And what's the turning effect about P produced by F? F into, say this is PD, F into PD, and that must just exceed the anti-clockwise turning effect produced by W about P. That means W about P is going to be W into PC, That's the underlying condition. That's the underlying physics in the problem. So F into PD, what's PD? PD is this length, which is R minus H, must be greater than or equal to W into PC. PC is this length, which is R square root R square minus R minus H whole square, right? PC, as you can see, is root R squared minus R minus H whole square, right? So root R squared minus R minus H whole square, right? That means F into R minus H must be greater than or equal to W into, this is root 2RH minus H squared. That means F must be just greater than or equal to W into root 2RH minus H squared divided by R minus H, right? That means what is F minimum? F minimum must be W into root 2RH minus H squared by R minus H. That's the minimum value of F for which this will climb the step, right? So this was an interesting situation on moments. To get a hang of what is happening in moments, what does one do for rotational equilibrium, for translational equilibrium, and the fact that if there is total equilibrium, you are entitled to take moments about any point, and algebraic sum of moments of about one point is 0, they would be 0 about any other point. These facts can be quick fixes to problems of a large variety. But then sure, we have a few more things to deliver. Promise to get back in a while. Thank you so much. Bye-bye.